Welcome, everybody. Today we will be looking at how to construct new groups based on given known groups. Um, so let's let so first let me look back at inner product, which we have seen before, but let me redefine that here. So let's let H and K be subgroups of a group G, and define the inner product of H and K by the following set. The inner product of H and K is denoted by HK, and it is the set of all elements X in G such that X is equal to H times K, where for some H in H and K in K. So basically HK consists of elements of the form consists of products of the form HK, where H is coming from H and K is coming from K. If we use the additive notation for the group operation, then we would be writing H plus K instead of HK. We proved earlier the following theorem. If G is an abelian group and H and K are subgroups of G, then HK is a subgroup of G. So again, if G is an abelian, so basically this theorem is addressing under what condition is HK a subgroup of G. Well, the first theorem tells here that HK is a subgroup of G if the inner product of H and K is a subgroup of G if G is an abelian group. Now, in here we proved this theorem when we talked about subgroups in an earlier video. We're going to generalize this theorem here. So here we're giving another condition for HK to be a subgroup of G. So here we're not requiring G to be an abelian group. So we're requiring G so G is any group and H and K are subgroups of G. And the condition that we are requiring here is that H inverse KH belongs to K for all H in H and K in K. And under this condition, then the inner product of H and K is going to be a subgroup of G. So before I start the proof here of this theorem, let's think about the condition here. So the condition here says H inverse KH is in K. Now this means that H inverse KH is some element of K. So let's say H inverse KH is equal to some element K prime of K. Now we can rewrite this equation as KH is equal to HK prime by if we multiply both sides of this equation by H, then we get this. So notice that think about this equation here. It's telling us that the elements of H and K almost commute. That is so here notice that I am bringing H on the left of K. We are bringing H on the left of K, and we can do that as long as we are okay with having another element K prime of K, not necessarily the same K. So this equation holds true. So we're going to use this in our proof. So So again, if I have a product K times H, where K is in K and H is in H, then I can bring H on the left of K as long as I am okay with changing K to another element K prime of K. Okay, so again, the statement of the theorem is right here. So we're going to start proving this. So let's let G be a group and let H and K be subgroups of G. So H is a subgroup of G, K is a subgroup of G. And we are assuming, let's suppose that H inverse KH is in K for all H in H and K in K. Clearly H is a non-empty subset of G because okay, I have a typo here. I should be saying HK. So clearly the inner product HK is non-empty because the identity, it belongs to HK. Why? Because the identity belongs to H, belongs to both H and K. So if I pick E in H and E in K, then E times E is in HK. So H is non-empty. Sorry, HK is non-empty. Again, I have a typo here. This should be HK. Now, assume that XY is in X and Y belongs to the inner product HK. Well, then we can write X as we can write X as H1 K1, where H1 belongs to H and K1 belongs to K, and we can also write Y as H2 K2, where H2 is in H and K2 is in K. Again, that's by definition of the inner product HK. So what we want to show is that XY inverse is in HK. And if we can do that, then by the subgroup test 2 that we proved earlier will tell us that HK is a subgroup of G. So now the goal is to show that X times Y inverse belongs to HK. Okay, so we have seen this. This is the condition of the theorem, and we know that the meaning of this condition is this, which we're going to apply here in the proof. And also, so far we picked X, Y in HK, and so we write X and Y as H1K1 and H2K2 respectively. And so these two statements are coming from the previous two slides. So since I didn't want to go back to the previous two slides, I'm going to put them here. And now I'm going to continue with the proof. So again, we want to show that XY inverse is in HK. Now to do that, we first observe the following. So XY inverse, so that means I have X is H1K1 and Y is H2K2. So I'm basically writing XY inverse here. Now H2K2 inverse is equal to what? Well, remember G is not abelian, so the inverse here would be equal to, oh sorry, I'm not applying the inverse yet, sorry. So I have H1K1 times H2K2 inverse. So the first thing that I'm doing here is the following. So I'm applying this this equation right here. So notice that if I have something like HK prime, then I can bring H on the right side as long as I am okay with having another element of K. So HK prime is the same as, I'm using this from right to left. So HK prime is equal to another element K in K times H. So H doesn't change here. It's just the K prime changes to K. So if I apply that to H2K2, then I can write H2K2 as some element K3 times H2, where K3 is in K. So H2K2 is being written in this way, by using this equation from right to left. So now I apply the inverse. So now this is the same as that. And here, the inverse of K3H2 would be the same as H2 inverse times K3 inverse. And now we're going to group together K1H2 inverse here. So K1H2 inverse here. Now, I am going to apply this equation again, but this time I'm going to apply it from left to right. That is, if I have K times H, I can bring H on the left of K as long as I am okay with having another element K prime of K. So K1H2 inverse, we can rewrite that. So K1H2 inverse, we can rewrite that as H2 inverse multiplied by some other element K4 of K. So instead of K1, so we are trying to switch these two elements here, these two factors. But if we do that, then we have to replace K1 by another element of K. So we could do this. So now we're going to group together the H's and the K's. And if we do that, then this is obviously an element of H because H is a subgroup of G. So it's closed under products like this. And K is a subgroup of G. So this is also closed under products like this. So then I see that this element is in H and this element is in K. So this product will belong to the inner product HK. So there we go. We have that XY inverse belongs to HK. And that completes the proof that the HK is a subgroup of G. So once again, let me go back to the statement of the theorem. So notice that the first theorem here is what we proved before, where the condition. So again, in both theorems, we are looking at conditions for HK to be a subgroup of G. And here the condition that we required was G is an abelian group, and here the condition we are requiring is this statement here, that H inverse KH belongs to K for all H in H and K in K. And then we saw that the meaning of this condition is also this. So you can see by looking at this that this condition is more relaxed than the condition that G is an abelian group. So this is a more general theorem than this. Okay, so one of the exercises that I want you to do is to prove the above theorem by using subgroup test 1, and you can go back to the presentation on subgroups and you'll see what the test is. So I want you to come up with with your own proof by using test 1. Here's an example. So let's say that the group G is DZ. That is, remember, this means this is the set of all multiples of D. H is the set of all multiples of A, and K is the set of all multiples of B, where D is the GCD of A and B. Okay, so D is the GCD of A and B. Then you can show easily that G is H plus K. So G is the inner product or inner sum of H and K. And we have done examples like this with specific numbers here before. So let me stop the video here since I want to keep the time under 15 minutes, and I'll see you in the next video.